the electric vehicle. You see one glide silently down the street and, the message feels so simple, so clear.
Hmm.
Zero emissions.
Exactly. Clean air, a future without fossil fuels. It's this powerful narrative that's really taken hold everywhere.
It has, but as we often find in these deep dives, the simple story, well, it rarely tells the whole story.
Right.
So our mission today is to look completely beyond the tailpipe. We've got a stack of sources here, life cycle assessments, UN reports, safety analyses, to do a full cradle-to-grave look at the EV.
And to be clear, we're not here to bash EVs. We're here to understand the full cost.
The total cost. Compared to a regular internal combustion engine vehicle, an ICEV, we're just following the data resource use, waste, and the geopolitical fallout.
Which forces us to ask a really uncomfortable question. Does that benefit of zero emissions on the road really outweigh the huge environmental and social debt you start with?
And who pays that debt? Because it's often not the person driving the car.
Okay, so let's unpack that. Let's start right at the beginning, on the factory floor. The moment an EV's life begins, it's already in what you call an environmental debt.
A significant one. The life cycle assessment data, the LCA, it really confirms this. The sheer resource intensity is staggering, and it almost all comes down to one thing.
The battery.
The battery. Making a normal car is heavy work, but an EV battery needs these, exotic energy-dense materials. It's a completely different scale of demand.
Okay, so give us that scale. When you say more resource intensive, what are we actually talking about?
Well, the numbers are pretty stark. EV production needs 6 times more natural resources than making a comparable ICEV.
6 times.
6 times. And that's because the ores for things like nickel, manganese, and cobalt have a very low metal content. You have to mine and process enormous amounts of rock and earth to get a tiny bit of usable material.
And if you're taking up 6 times the material, I have to assume you're also creating 6 times the waste.
You are. That resource use translates directly into waste at the source. The production of one EV generates 6 times the mass of industrial waste. We're essentially trading millions of little tailpipes for a few, massive pollution sites at mines and refineries.
So we're talking about giant piles of waste rock, tailings dams. But what about the stuff we can't see, the atmospheric costs?
Also heavily front-loaded. The emissions of harmful substances, not just CO2, are about 1.5 times greater during EV production.
And why is that?
It's the energy needed, specifically for producing non-ferrous metals, like the aluminum you need to make the car lighter to offset that, incredibly heavy battery.
Okay, and now for the big one, the very thing EVs are supposed to solve. What about greenhouse gases during manufacturing?
The initial carbon debt is very real. An EV's production emits about 1.65 times more CO2 than an ICEV's. Again, it's the high energy demand for the battery cells and aluminum.
So an EV has to be driven for thousands and thousands of miles on a clean grid just to break even on carbon.
Exactly, just to pay off that initial manufacturing debt.
Let's drill down on one of the most, I think, shocking impacts from the sources. Water. The water consumption for these raw materials it's a massive global problem.
It is arguably the most stunning data point in the entire LCA. Lithium. It's essential for our current batteries, and the way we get it uses unbelievable amounts of water.
How much are we talking?
To produce just 1 ton of lithium, enough for maybe 100 car batteries, you need around 2 million tons of water.
2 million tons of water. Just to help you visualize that, that's enough to fill 800 Olympic-sized swimming pools. Yeah. For 1 ton of lithium.
And the consequences are already playing out. Look at the lithium triangle parts of Chile, Argentina, Bolivia. These are arid regions experiencing severe water depletion. In one part of Chile, mining operations use up something like 65% of the region's entire water supply.
And it's not just that the water is disappearing, it's that the water left behind is getting contaminated.
Right. The process pollutes what's left. So you see protests popping up all over the world, Nevada, Tibet, the Philippines. All of them are about polluted waterways and depleted groundwater linked directly to mining for battery materials.
This really brings up that spatial separation, right? The cost is paid in one place, and the benefit is enjoyed somewhere else entirely.
And that takes us from an environmental problem to, really, a geopolitical and social justice problem.
How so?
The UNCTAD data is painfully clear. Most EV consumers live in wealthy, industrialized nations. But the raw materials, they're concentrated in a few developing countries that often don't have strong environmental or labor laws.
And what's the textbook example of this?
Cobalt. Without a doubt. Some people call it the blood mineral of the EV era. Almost half the world's reserves are in one country,
The Democratic Republic of the Congo.
the DRC. The DRC. And it accounts for over two-thirds of all global production. So you have Europe, the US, China, all critically dependent on this one, very politically unstable source.
And the human cost there is something we just can't ignore in this conversation.
No, you can't. The sources are harrowing. They estimate around 20% of the DRC's cobalt comes from so-called artisanal mines.
These aren't big industrial sites.
No, these are unregulated pits. People, including an estimated 40,000 children, digging with their bare hands in incredibly dangerous conditions. Toxic dust, tunnel collapses, earning maybe a couple of dollars a day.
So there's the paradox. The clean part of the EV, the quiet streets, the tax credits, that's all enjoyed in affluent cities.
Mm-hmm.
But the dirty, dangerous part, the mining, the pollution, the child labor, that's all exported to some of the most fragile places in the world.
It really makes you question the whole premise. If a country pushes for a rapid EV adoption, but doesn't have the ability to mine, refine, and build those batteries cleanly at home,
It's basically just mandating the export of its environmental and social problems.
and it creates this huge geopolitical lever for the countries that do control that manufacturing capacity. This isn't just an environmental debate, it's a fierce industrial policy fight.
It's about who owns the future of manufacturing.
Absolutely. The green imperative is the public reason, but behind it, you see the vulnerabilities of nations that jumped in without securing their own supply chains first.
Okay, let's shift gears. Let's say the EV is built, it's paid off its carbon debt, and it's on the road. The story still isn't over. Even with no tailpipe, there are some counterintuitive operational problems.
That's right. The LCA shows it's a series of trade-offs. Take air pollution. The data we have says that during operation, an EV can be responsible for 3 times higher harmful substance emissions into the air than an ICE EV.
Wait, hold on. How is that possible with zero tailpipe emissions? That makes no sense.
It's where the electricity comes from, the old smokestack effect. If your grid is burning coal or natural gas, the power plants are often less efficient at turning that fuel into motion than a modern car engine is. So the total pollution from cradle to wheel is actually higher.
So the pollution just moves from the city street to the community with the power plant.
It's relocated pollution. Unless your grid is almost entirely renewable, that EV is still polluting.
And that's not the only emission, is it? What about just physical wear and tear?
We have to talk about non-exhaust emissions, NEs. This is critical. The NIH, the National Institutes of Health, their research shows that these emissions from brake dust and tire wear now make up to 90% of all particulate matter from vehicles.
And particulates are directly linked to vehicle weight.
Exactly. And here's the battery problem again. It's a huge weight penalty. An EV is just heavier than a comparable gas car. So even with regenerative braking saving the brake pads a bit, the tire wear and road abrasion are much worse.
So we might not actually be reducing particulate pollution at all. In some cities, we might even be increasing it.
It's possible. We're trading chemical pollutants from the tailpipe for physical pollutants from the tires. And under hard acceleration or braking, the generation of these tiny nanoparticles can surge by almost 99%.
We're swapping one type of airborne toxin for another. Which brings us to, I think, the most catastrophic risk of all. Thermal runaway.
The EV fire?
We've all seen the videos. They look impossible to put out.
They are incredibly difficult for first responders. The stats are sobering. An EV fire takes about 8 times longer to suppress, needs 2.5 times more people, and this is the amazing part, 110 times more water.
110 times.
Up to 110 tons of water for a single car fire. It's a massive strain on any fire department.
And it's not just the fire, it's what the fire releases.
This is the immediate life-threatening danger. Thermal runaway releases a cocktail of toxic gases. The worst one is hydrogen fluoride, HF.
Okay, what does that mean in real terms?
A standard 100 kilowatt battery fire can release between 2 and 20 kilograms of HF gas. That amount is calculated to be anywhere from 80,000 to 800,000 times the level considered immediately dangerous to life or health.
800,000 times the lethal limit.
This isn't an irritant. It's an acute lethal poison. It's an extreme hazard for anyone nearby, especially firefighters.
And what about that 110 tons of water you just sprayed on the car? Where does it go?
That's the final environmental nightmare. The water is essential to cool the battery and scrub the toxic gas from the air, but the runoff, that water, is now a highly corrosive solution of hydrofluoric acid.
So you need a hazmat team.
Immediately. You have to dam and dike the area to contain the toxic runoff before it contaminates the ground and the water table. The toxicity from the manufacturing phase meets the acute toxicity risk of the operational phase in this horrifying event.
So given all of this, the supply chain problems, the huge upfront environmental costs developed countries are now starting to react with policy, right? They're trying to regain some control.
Yes, and you have to see this as a strategic necessity. They're using regulations to force transparency and sustainability because they realize they've lost control of the industrial process.
The EU's new battery regulation seems to be the prime example. It feels like they're trying to claw back some ground.
It's a sweeping piece of legislation. It imposes very high standards precisely because these economies now see their dependence on imported low-standard materials as a huge economic risk, not just a moral one.
So what are the key rules here?
Two big things. First, due diligence mandates. Starting in 2025, companies have to audit their entire supply chain for cobalt, lithium, nickel.
A problem minerals.
Exactly. And they have to publicly report on any environmental or human rights issues. It's a direct shot at the problems we see in places like the DRC.
So if you want to sell an EV in Europe, you have to prove your cobalt isn't mined with child labor.
You have to prove it. And the second piece is the digital battery passport coming in 2027. It's like a digital twin for every battery, permanently tracking its carbon footprint, its material origins, everything.
Making that hidden upfront cost visible.
Exactly. And finally, they're demanding circularity. They're setting really ambitious recycling targets.
So forcing the end-of-life grave phase to become a new beginning.
Right. They're mandating things like 90% recovery for cobalt and nickel by 2027. This is a clear attempt to build a local, cleaner recycling industry because, frankly, they don't have one right now that can compete.
So this is about more than just being green. This is industrial strategy.
Absolutely. It's using high environmental standards as a barrier to entry. It's a way to try and reshore an industry they've largely lost control of.
So for you listening to this, what's the big takeaway? It's that the EV transition,
Yeah.
it's not just a simple switch from gas to electric.
No, it's a fundamental shift.
Yeah.
You're trading a distributed tailpipe emissions problem for a highly concentrated manufacturing toxicity and geopolitical problem.
So the path forward has to focus on fixing that beginning phase.
It has to. Using clean energy to build the batteries, for one, and developing new materials that are less toxic and less concentrated in one or two countries, maybe sodium-ion or solid-state batteries. And we have to get serious about recycling and second life uses. An old car battery still has 70 to 80% of its capacity. It's perfect for storing energy on the grid.
When you step back, it's pretty clear. Right now, EVs have a higher environmental impact on almost every metric.
Yep.
Resources, waste, toxicity, water use, production GHGs. The only win is operational GHGs, and even that depends on a clean grid.
Which leaves us with a final provocative thought for you to consider. At what point does a nation's ability to manufacture EVs cleanly domestically with a fully transparent and ethical supply chain become the only true measure of a green industrial policy? If a country mandates a technology but outsources all the pollution, the water depletion, and the labor abuses that go with it, what does that say about their commitment to sustainability? That's the real burden we're now placing on the EV.